Hello, everyone. Good afternoon. Good afternoon, everyone. Welcome to the class. Now, before I start, I'm going to take your attendance first. And can I check with you that you can see my screen and you can hear me? Yes. Okay. Thank you. All right. I'm going to take attendance first. So if you're here, just say yes. Lor. Okay. Okay. Dong is here. Lo Tiong Lia. Tiong Lia, are you here? Okay, Lu Jui Min. Han Xiang. And Han Xiang, are you here? And Han Xiang. Okay, Ng Wei Hong. Ng Wei Hong. Right, good afternoon. Ong Mei Lin. Ong Mei Lin. Okay, Pung Sui Wen. Pung Sui Wen. Okay. Hua Yi Hang. Hua Yi Hang. So Yen Chang. Okay, good afternoon. Tan Xin Shin. Okay. Tio Leong Ho. Tio Leong Ho. All right. Tio Yi Si. Wong Chung Yi. Wong Ka Shing. Yong Wing Liang. Right. Yong Chi Ye. Yong Chi Ye. Uh,
Yes,
oh, okay, you're here. Okay. Excellent. Everyone is here. Tiong Lia, are you here? Lo Tiong Lia, are you here? Uh, wait. Oh, Tong Lia is in group one. Oh, yeah. Okay. So is in one. Right. Okay. So yes, he's in group one. Okay. So this would not be counted. 16. Okay. Excellent. Everyone is here. Thanks. All right. Now, we're gonna start our tutorial. So this is our first tutorial, and our first tutorial is a review of computer engineering basics. So it's basically a review of stuff like, okay, first of all, you did uh, uh, you did digital electronics. Okay, then you did digital system design. Okay, so digital electronics, you learn about uh, logic gates and flip-flops. Okay, so logic gates are built from transistors. So at the lowest level, you have transistors. So you add 4 to 6 transistors together, you wire them together, you get a logic gate. Okay, and you wire a few logic gates together, right? You get flip-flops. To flip-flops retain information. They are called memory elements. And you use logic gates and flip-flops to build two types of circuits: combinatorial logic circuit and sequential logic circuit. So combinatorial logic circuit has no memory, right? It's basically a collection of logic gates that will convert an input to an output, and you design it using K-maps, truth tables, and then you simplify to equation, sum of product or product of some equation. Then you implement it using logic gates and flip-flops. Okay, so that's what you did in digital electronics. And then in digital system design, you design more complex uh, circuits. When you design more complex circuits, circuits with a lot of variables, it is not practical to use K-map and truth table anymore. K-map and truth table maybe maximum four variables. 5 variables is very difficult, right? So instead of using K-map truth table, you use hardware description language, VHDL. The VHSIC hardware description language, short is VHDL. Okay, so you describe the function of a circuit using HDL, and then you implement the design on FPGA, this special chip that you can program the interconnections between logic gates and flip-flops inside to build a digital circuit. Okay, so now, what is the most complex digital circuit? The most complex digital circuit is a microprocessor. So then the next subject you learn is microprocessor. Microprocessor is the most complex digital circuit. It is the heart of your computer system, right? So then you studied you studied the basic microprocessor concepts using the PIC microcontroller. Okay, assembly language and processor architecture you studied in the subject microprocessor. And then you go one step further, you studied computer architecture, computer architecture, where you learned about more advanced features of a processor. Most importantly, being pipelining and parallelism. So you can exploit certain operations that can be performed in parallel because they are not related to each other. So you call that parallelism. And then you have a pipeline, which is the key component inside your computer's control unit, right? Which can speed up processing. And then you learn about memory architectures and so on. Okay, so now we link all of these concepts together in this subject, embedded systems. We link all of these concepts together, and also we make use of your C++ programming knowledge. C++ programming knowledge. Okay. Now C, we call it C/C++ because C came out first. C came out first in the 1970s. C came out first. It is a sequential programming language, right? And it is very closely modeled after assembly. The first programming language was assembly. But the problem with assembly language is it does not have structure. Assembly programming doesn't have structure. Your whole program is just a long sequence of assembly instructions. So when your program is very big or it's very difficult to understand, so the next step would be the programmers thought of why don't we add structure to the program? What we mean by structure is imagine you read a storybook, a 1,000 page storybook. The storybook has no paragraphs and no chapters. So you read a 1,000 page book that has no paragraph and no chapter. You read 1,000 page all at one go. Very difficult, right? Now, the book becomes more easier to read if you split the whole book into maybe 20 chapters. And then each chapter got maybe a few sub-chapters. And then inside each sub-chapter, you got paragraphs. Okay, and each paragraph maybe got a few important points, key points, bullet points. This structured approach makes the whole program much easier to read, right? So it's the same with C language. C language introduced the concept of functions. Functions. So you you encapsulate code, you group them together into functions. So each function performs a specific operation. And when you write a C programmer, you should never write a function that is longer than one page. This is a good programming practice. Imagine your computer screen, one page, one A4 paper maybe. One function should do at most 4 to 5 subtasks. Right? A function does one operation, but this operation maybe consists of a few subtasks. So a function should perform maximum of 4 to 5 subtasks, and it shouldn't be longer than one page. Why? The reason is because the human brain, we can only process information. Our human brain cannot process a lot of information. So at any one time, you can only focus on the information that can fit on one page. If more than that, you start to get confused. So if your coding for the function is longer than one page, what do? Then you break it into smaller functions. Okay? And the heart of C program is functions. When you run a C or a C++ program, the first function that runs is your main function. Then the main function will call other functions, and these other functions will further call other functions. So your entire C program is just a lot of functions that can be all inside one source file, which is not a good idea. It's better to split it into separate source files. Each source file groups together some specific functions. Like for example, let's say you want to write a program, LCD and keypad, simple LCD and keypad. So you should have one source file to put all the functions for the keypad. Then we call that keypad.c. And then you should have one source file to put all the LCD functions. So we call that lcd.c. Okay, and then you have your main.c. Main.c will call the LCD and the keypad functions which are in keypad.c and lcd.c. So how does the main function link to these two uh, files? Then in your main function, so this is your main.c source code. When you write your program, main.c. So you will write at the top hash include lcd.h and include keypad.h. Okay, so you include these two header files. You include these two header files, and they will link your main.c to these other source files. Right, so it's just a collection of functions. Now, C++ is a larger set of C. C is a subset of C++. So if you already learned C++, basically you know everything there is to know about C. Okay, so you will need all this knowledge when you're writing programs for embedded systems. Okay, so now let's do a quick review of the basics of the stuff that you learn in all these subjects. First of all, let's start with question one. Um, Explaining some important terminologies. So we have IC, IO, ALU, CPU. What are these guys? Okay, right. So let's look at the first question. Right. Oh, by the way, you don't need to copy or record anything because this tutorial session I just discuss and talk with you. So if you have any questions, you can ask. It's quite informal. It's not just me talking. You can ask me a lot of questions. I monitor the messages here, so you can ask me a lot of questions. Right? I will upload all the tutorial answers at the end of the week because there are a few groups. So at the end of the week, after we have gone through all the tutorial sessions, I will upload the tutorial answers, okay, which are much more than what I write here, more detailed. So here I just talk with you informally on discussion, face-to-face discussion. Okay. Okay. So question one, what is IC, IO, ALU, and CPU? Okay, first of all, what is IC? IC is integrated circuit. What does it mean by an integrated circuit? An integrated circuit is now back in the 1960s, when you build a circuit back in the 1960s, so you have a printed circuit board. Okay, then you want to build a circuit, so you got resistors, you got connectors, and then you got some ICs here. Not IC, don't draw IC. You got some transistors here, and then some diodes, some capacitors, some inductors. Okay, so if you want to build a circuit, you have to use all these. We call these discrete components. Discrete components. So you have to wire all these discrete components together. So underneath this printed circuit board, underneath there are a lot of copper tracks. So there are a lot of copper tracks underneath. A lot of copper tracks. So this is how you build your circuit. It's very big, very power consuming, not very reliable because these components, some of them may break, not very reliable. So the breakthrough came when somebody successfully integrated all these components, placed all these components onto a single piece of silicon, onto a single piece of silicon like this. So all these discrete components are integrated, put together, right, and placed onto this single piece of silicon. So this is your integrated circuit. Now, an integrated circuit is a piece of semiconductor containing your entire electronic circuit, and it needs to connect to external circuit. Okay, this is your integrated circuit. By itself, it cannot work on. You need some external circuitry. At least you need to provide power and stuff. So how does this integrated circuit connect to the external circuit? So you need I/O pins. So these are your I/O pins, And your integrated circuit connects to the I/O pins using some gold wire, very common. Using gold wires, it connects like this, right? And the other side also. So you have that, and then it connects. Okay, so this is an integrated circuit. Now this guy, you draw it bigger, draw it bigger. It looks like that. So this is your circuit, right? And these are your I/O pads. The I/O pads are very big because that's where you will solder these uh, wires. Of course, you can't solder it by hand. Why you can't solder it by hand is because imagine this is your thumb. This is your thumb, and this this guy, this guy is probably this big. Okay, very small, right? Very small. This one is probably like that, very small. So you have a machine to pull the wire and then solder. The machine is a very fine needle point soldering iron. You solder it here, right? It's very fine. Okay, so an integrated circuit is a semiconductor containing complete electronic circuit placed inside a protective packaging. This is your protective packaging, right? With pins to connect it to external circuit. Okay. Now next one is I/O. Next one is I/O. So let's talk about the integrated circuit which we are interested in. The IC that we are interested in is the microcontroller. So the IC that we are interested in is the microcontroller. Now, the key parts of a microcontroller is the processor, memory, and peripherals. Okay. If you look at the three main components inside a microcontroller, it is the processor, peripherals, and memory. There is one more block, but it's miscellaneous. Miscellaneous. So we call it a supporting circuitry. Supporting circuitry. Okay. So the CPU, the CPU fetches instructions and data from memory. It fetches instructions that tells it what to do, and then it will carry out the operation. Okay. And the microcontroller is not like a computer. Microcontrollers doesn't do uh, data processing exclusively. Microcontrollers don't exclusively only do data processing. What they do is control. Okay, they control. So in order to control, your microcontroller needs to interface with the external physical world. It needs to interface with the external physical world through peripherals. Through peripherals. Okay. Specifically, specifically the peripheral, we call it one type of peripheral, GPIO, general purpose IO port, GPIO. So in your PIC microcontroller, you have port A, port B, port C, port D, port E. In your 8051, you call it port 1, port 2, port 3, port 4. So got different names, but generally, the generic name is GPIO, general purpose IO port. This is called a parallel port. You can control, set and clear each pin individually. Now, there are many other types of I/O ports. For example, ADC, analog in, DAC, analog out, serial ports. Those are other types of I/O ports. But the most basic one is GPIO. Okay, and GPIO is your this input output. The reason is because your processor does not have sufficient voltage or current to control external devices. The processor's signals are very low voltage and low current. So you need this special circuitry here, this GPIO circuit. It will perform, it will allow the low voltage, low current processor to switch on and off higher voltage and higher current devices outside the outside this microcontroller. Okay. All right, so we have a basic idea of peripherals, CPU, and memory. Now, supporting circuitry is, for example, your reset circuitry, your power management circuitry, and your clock circuitry. These are the supporting circuitry, basic ones. Must have one. You have the circuitry to uh, regulate and stabilize the voltage, regulate and stabilize the clock signal from external oscillators, or there might be internal oscillator, and you also have a reset signal, a circuit to handle reset input, external reset input to the microcontroller. Okay, so these are all the basic parts inside a microcontroller, and the key one is this I/O port, input output. Okay, now let's look in detail at this ALU. What is ALU? What is ALU? ALU is the heart of your computer. So if you look at this CPU, you look at this CPU, right? You look at this CPU, right? So a computer is called a computer because it performs computing functions. What is meant by computing function? Computing functions are arithmetic and logic operations. So a computer can compute because it has a circuit called the ALU, arithmetic logic unit. This circuit performs all the arithmetic, subtract, multiply, divide, add, and logic. Logic is your N or not X or uh, left shift, right shift, rotate, and move operation. Even the move operation is considered a logic operation. So this is the basic operations that a computer can perform. Right? This is the atomic level of computer operation. If you look at the physical world, you got a lot of things around you: tables, chairs, trees, cars, right? All these things you can divide them until you reach the smallest level, which is atoms. Okay, and is indivisible anymore. Atom is the Greek word for indivisible, cannot divide any further. So that's the smallest part of physical materials. The smallest part of a computer program is the LU operation, indivisible. So you see all the fancy things like your CGI movies or the computer games that you play or all the computer programs that you use. If you divide it down to the basic level, at the end, at the lowest level, it is just arithmetic or logic operations. But the computer is so powerful because it can carry out trillions of these operations per second. Trillions of these operations per second. Okay. Uh, is it trillions? Gigahertz is sorry, billions. Okay? Billions. It can carry out billions of these operations per second, not trillion, billions of these operations per second. So that's what makes it so powerful. Okay. So the arithmetic logic unit is the circuit that performs the actual computing functions. And how does it do it? You feed it with two data one, data two, and it produces a result. Okay, that's all that it does. So if you say that you have a 8-bit CPU, if you say that you have a 8-bit CPU, then basically you're operating on two pieces of 8-bit data and you produce an 8-bit result. So if you say you have a 16-bit CPU, then uh, it just means that you have a 16-bit ALU which can operate on two 16-bit numbers at one time and produce a 16-bit result. Okay, so desktop computers now are 64 bits. Microcontrollers are up to 32 bits. You don't need higher than 32 bits from your controller side. It's not practical that type of processing power because if you go above 32 bits, yes, you have a lot of processing power, but the processor also consume a lot of energy. When the processor consumes a lot of energy, it's going to heat up. When the processor heats up, then you're going to need to cool it down using heatsink or other forms of cooling systems. This will increase the size and cost and power consumption of the whole device. So it's not practical for that. And that type of processing power is also not required. So microcontrollers are generally 8 bits or 32 bits. 16 bits is something in between that is not, that is rarely used. Okay, and the most popular 8-bit microcontrollers are PIC microcontroller. The most popular 32-bit microcontrollers are your ARM Cortex microcontrollers. Okay, so you studied both in your syllabus. Earlier in microprocessors, you studied 8-bit PIC microcontrollers. Now you study 32-bit ARM microcontrollers. Okay, so that's the ALU. This is the ALU. And the ALU, yes, here's the main character. Here's what makes a computer. But the ALU cannot operate by itself. The ALU is just one part inside the CPU. You have other things inside the CPU that supports the ALU. What are they? First of all, where does the data that the ALU operate on comes from? The data that the ALU operates on comes from registers. So you have registers. Okay, so this data that the ALU operates on, it comes from registers, right? And then when the ALU produces a result, the result will be stored back into registers. So these registers are temporary storage location of information inside the CPU. They are the highest speed, very fast, but they are big. So you can't put a lot inside the CPU. That's why you have to have additional memory outside the CPU that you implement as SRAM, data memory. Okay. Now, the ALU performs operations. The ALU performs operations, but where are those operations? So those operations are stored in memory. Is out this memory outside your CPU. So in order for your CPU to access memory, it needs a memory. It needs a memory controller. It needs a memory controller. So the CPU will tell memory which uh, location it wants to access, and then it will either read the value back or it will write the value to memory. So this is the data. Okay. And now if it's an instruction, if the if an instruction is fetched, so it can be data or instruction. Which brings us to two types of architecture. Two types of architecture. So you got the von Neumann architecture and you got the Harvard architecture. Okay, what's the difference? Von Neumann architecture uses a single bus for data and instruction. That means you can only transfer data or transfer instruction at any one time, but not both. Harvard architecture, you have two separate buses, two separate sets of wires, one set for data, one set for instruction. So Harvard architecture, you can fetch instruction and rewrite data at the same time. Okay, so in other words, Harvard architecture will have higher performance than von Neumann. But Harvard architecture, the processor design will be more complex because you have two sets of buses. So more complex processor design means more expensive, bigger, use more power. For Neumann processor designer, simpler, smaller, use less power. So got both also got their applications. Okay, both also got applications. All right. So you fetch and let's say you fetch an instruction. You fetch an instruction. The instruction will be stored temporarily inside a special register called the instruction register. Now, why do you need to store it temporarily inside this instruction register IR? Because you have a special circuit here called the control unit and instruction decoder. So the instruction decoder circuit is just a combinatorial logic circuit, right? You will feed the instruction stored in the instruction register to the instruction decoding circuit, and then the instruction decoding circuit will output control signals to carry out the appropriate action. Okay, so this is your control bus. So the control unit will output signals uh, to tell the ALU which operation to perform, to tell the register bank which register to be read or written to, and to tell the memory if this instruction is read or write to memory and you need to access memory again for some data. So this is the control bus, right? And on this side, this is the internal, the processor's internal bus inside the processor. Okay, so this is the central processing unit. The central processing unit is basically the arithmetic logic unit plus some supporting circuitry that allows the ALU to function as a computer. Okay, so in order for the ALU to work, to do its computing job, it needs these guys to support him at a basic level. There are a lot of other things, but these guys must have register, memory controller, control unit, instruction register, ALU must have. Okay, all right. So this is we talk about IC, IO, ALU, CPU. All right. So the next question is uh, what is an embedded system? What is an embedded system? What is an embedded system? Why do you call it embedded? The reason you call an embedded system uh, embedded is because embedded systems are products. Embedded systems are products. It is a product. Okay, an embedded system, remember, is a product. It is a product that provides a useful function. Okay, all embedded systems are products that are designed to provide a useful function to the user. For example, the electric hot plate to heat up food. So the electric hot plate, the useful function is to heat up food. How does the user use use this product? In order for the user to use the product, the user must be able to interact with the product, right? Interact with the product. So the product needs to have a user interface. Okay, it needs to have a user interface. There is no such thing as a product without a user interface. A user interface can be as simple as a button, an LED, or a knob that you can turn. Okay, so here the user interface is just a knob that you can turn to adjust the temperature, and maybe an LED to show you that the product is working. Right, basic user interface. And how does the product provide the useful function? So in order for the product to provide the useful function, it will have two types of things. It will have sensor and actuator. Sensor to input, actuator to output. Okay, sensor to input and actuator to output. Let me just draw this nicely. Okay, like this. This is your function. Okay, so the sensor in this case, the sensor in this case is your temperature sensor. The actuator in this case is your heating element. Sensors are defined as devices that convert physical change to electrical voltage or current. Sensors convert physical change to electrical voltage or current. Actuators convert electrical voltage or current to physical changes. In this case, is converting electrical power to temperature changes, heating element. Okay, so all these things, sensors, actuators, user interface, they are all controlled. They are all controlled. They are all controlled by a controller. So you have a controller here. And this controller has a processor inside. Okay, we call this controller a microcontroller. It has a processor inside. It has this CPU embedded inside. So we say that this is a processor processor embedded embedded within the product to. Why do you want to embed a processor within the product? To control it. Why you want to control it? To provide useful function to the user. So this is what an embedded system is. An embedded system is any processor that you embed, you place inside a product to control the product to provide some useful function. You see, as a user, when you use the product, you are not using the processor. As a user, when you use this product, for example, the electric hot plate, you are using its function to heat up food. You don't use the processor inside, okay? As compared to a desktop computer. Now, a desktop computer, what is its function? Computing, processing. So you are using the processor directly. That's the main difference between embedded system and desktop computing systems. Desktop or laptop computing systems, you use the processor directly to run programs, to process data. Okay, embedded systems, you do not use the processor directly, but you use the function provided by the product. Okay, so this is how you would describe an embedded system. A processor embedded within the product to control it, to provide a useful function to the user. Okay, which brings us to the next question. What is the difference between a microprocessor and a microcontroller? Okay, what is the difference between microprocessor and microcontroller? So the difference is just that. The difference is just that. Here I have a chip. Here I have a chip. How about radio and TV? Are they considered as embedded system? If the radio and TV has a processor embedded inside, then it is an embedded system. Okay, you can have analog radios and you can have analog TV. If analog radio means your radio is built from transistors and op amps. Analog TV is you have some uh, digital controllers, some ICs, but they are not programmable. There are some digital chips that will control the old type of TVs, the cathode ray tube, and show you images and sound. So this doesn't have a processor inside. So the keyword, that's a very good question. The keyword is processor. In order for a product to be called an embedded system, it must have a processor inside. Okay. So what is the difference between a microprocessor, CPU, a microprocessor, and a microcontroller, MCU? What is the difference? What is the difference between these two guys? So these two guys are integrated circuits. What is the difference? The difference is the CPU inside the logic circuitry is entirely CPU, nothing else. So it's a very powerful processor. Microcontroller, you got CPU, you also have memory, and then you have GPIO ports, and then you have a lot of other peripherals like ADC, DAC, PWM, etc. You have a lot of things. And all these things combined together, to give you a complete computer system. So if you want it to work, you just need to apply power. You just apply VDD, VSS, 5 volts or 3.3 volts in ground. It will start working. You don't need anything else. But for the CPU, you need to connect external memory. You need to connect external I/O ports. You need to connect external power management circuitry. Okay, like your power supply, you need PSU, or you need a lot of stuff in order to support this guy to work. But this guy is very powerful, very general purpose. That's the key difference. CPU is so powerful because he's an overkill solution. Overkill solution, so you can use it for any application, any function. The microcontrollers are optimized for a specific application, optimized in terms of size, power, cost, energy, materials, optimized for a specific application. Why? To get the maximum function with the lowest price. Because it's a product. We need to sell it. Okay, so we will choose the mouse controller the cheapest mouse controller that best meets our needs. So that's the difference between CPU and MCU. Okay, all right. Okay, welcome. Next question. What is the range of numbers represented by 16-bit ALU? What is the range of numbers that can be represented by a 16-bit ALU? 16 bits. 16 bits. Okay. So here, if you have a 8-bit, 8-bit, 8 bits, 8 bits means 8 bits just means that you have is the wire 8 bits. It just means that you have 1, 2, 3, 4, 5, 6, 7, 8, 8, 8 wires, right? Uh, so these 8 wires you can carry, let's say 1011, 1011. So any number between 00000000 to 11111111, which is any number between 0 to 255. Or we can generalize. We say 0, 0 to 2 to the power of 8 minus 1. Or we can generalize and say 0 to 2 to the power of n minus 1, where n is the CPU size. Okay, so if the CPU size is 16 bits, so if n is equals to 16, then the range of numbers that the processor can deal with is 0 to 2 to the power of 16 minus 1. Okay, so if you're familiar with uh, digital numbers, 2 to the power of 16 is a very common number. It's 65536. 65536. So if you minus 1, then you get 0 to 65535. Does that mean that we can only deal with this number size? No. Actually, you can combine multiple 16-bit numbers. If you combine two 16-bit register, you get a 32-bit number. Okay, you have 8-bit 8-bit registers here. You combine four 8-bit registers, you get a 32-bit number. You combine eight 8-bit registers, you get a 64-bit number. So you can combine them, but the operation will be slower because the ALU can only operate on 8-bit at any one time. So you need multiple operations just to deal with one 64-bit data if you're using 8-bit CPU, for example. Okay. Right. Now, some trivia here. Some trivia. 65535 is called 64K. So in embedded systems, 1K is not 1000. 1K is not 1000. 1K is 2 to the power of 10. Right? 1K is 2 to the power of 10 or 1024. Right? So don't get confused with this. 1K in digital systems is 2 to the power of 10 or 1024. That's why when you take 64 multiply 1024, you get 65536. Right? Which is also known as 64K. You're wondering, 64,000, why becomes 655,361? Because it's not 1,000, it's 64 times 1024. Okay, right. Coming back to this question. So, what is the range of number that can be represented by 16-bit ALU? 0 to 65535. 65535, because you include 0, right? Okay, next one. What is a bus? What is a bus in the context of embedded systems? Describe two types of buses that you can find in embedded system. What is a bus? What is a bus? Okay. Uh, why do we call it a bus? Why do we call it a bus? Now, why do we call it a bus? So I use orange color. Okay, so it's a bus. Bus. Okay. Now, if you think about a bus, if you think about a bus, what do we normally see in a bus? So you see a lot of people inside the bus. Okay, you see a lot of people inside the bus. Okay, and my question is, what does all these people have in common? All these people inside the bus. What do they all have in common? What do you think? You have a bus here. You have a lot of people inside. Why do they take a bus? Why don't they take? Yeah, they are traveling. They are traveling. But what do they have in common? They are traveling. You can travel with a motorcycle. You can travel with a car. But why bus? Because there are a lot of people inside. So what does all of these people have in common besides traveling? What do all of these people have in common? They all probably got onto the bus from the same bus stop, right? And they are all going to the next same bus stop. That's why you call it a bus. Because everyone in this bus, everyone inside here that they came from the same source and they are going to the same destination. In other words, that they are all related. Okay, so in a computer system is built from a lot of subsystems. A computer system is built from a lot of subsystems. Just now you look at the CPU. You have a lot of subsystem even inside the CPU. So you got registers. This is a subsystem. ALU is a subsystem. Memory controller is a subsystem. Control unit is a subsystem. So there are tons of subsystems, and all these subsystems they are connected together by buses. Okay, they are connected together by buses. So buses are just the collection of wires for data exchange between subsystems. Okay? Any complex digital system will have a lot of blocks. So each of these blocks performs some specific operation, and they all need to exchange information. And the information is not just one wire, it is a collection of wires. This collection of wires carries information and clock signals, data and clock signals. They are all related. Okay? They are all related. So we call this set of wires a bus. So a bus is a set of interconnections that is dedicated to provide data exchange between subsystems inside a computer system. Okay, that's a bus. That's why. So whenever you see bus, think of this. That's why it's called after. Right. Okay. Um, Next one. Describe the term instruction set and how it is different for high and low level programming. Okay, basically, high level programming for example, C, Python, Java. Okay, high level programming is, for example, C, Python, Java. When you do high level programming, you use keywords that is like normal English words. If, then, else, for, this type of English words. Okay, when you do high level programming, you use English words. So your programmer is more easy to read. But in order for the processor to run your program, you need to compile. Compile means to convert your high level program from those English sounding keywords to the instructions that the processor can understand. Okay, so if you program in high level language, you have to compile your program, convert it to instructions that the processor can understand. Low level programming means you are writing your program directly using those instructions. In other words, low level programming is assembly programming. Okay, no need to compile. No need to compile. You're using the instructions that the processor can understand directly. That's the difference of high level and low level programming. Okay, so why do we still do low level programming nowadays when high level programming is so easy? That's because each processor is different. Each processor is different. It can do very specific operations that is specified by its instruction set. High-level programming languages, C, Python, Java, they are very general purpose. Okay, they are general purpose that do general things. And these high-level programs, they cannot do certain special operations that the processor is capable of. So in order to access those special operations, what are they? Example, put the processor to sleep. If you want your processor to power down, put it to sleep, you have to execute some special assembly instructions. And there is no equivalent in high-level programming. High-level programming, you cannot access one, so you have to program in assembly. Okay, and this is one of the main reasons of using assembly. Other reasons is there are certain operations that uh, you cannot get it to work using high level programming. Okay, you have to write it in using assembly instructions because, for example, you want it to run very fast. You want it to run in a certain way that the compiler just won't generate for you, because you need to get the compiler to generate the assembly instructions for you. But no matter how, sometimes it happens, no matter how you write your C program, the compiler just won't generate the assembly instructions that you want, it will do something strange. Very rarely, but it happens. Then you will need your skill in assembly language to manually code that section in assembly. Right? It's very important also for debugging because sometimes the compiler doesn't generate the assembly instructions to do what you intend it to do. So then for that part, you have to manually code it. And you also need to be able to read the code to understand why it's wrong. Read the assembly code. Okay, so that's the difference between high and low level. What are the main steps in program development cycle? If you want to develop a program, what are the main steps? So the main steps is basically just is very straightforward. You write the code and then you build. Build means compile the code, convert it to assembly instructions, and then to executable. You build. So if you build, you get any syntax error, then you have to check your code again. If you build no errors, then it's time to simulate, test, debug. If any errors, go back and check your code. If no errors, then so this is the difference between embedded systems and between engineers and IT guys. IT guys, programmers, computer scientists, software engineers, what they do is they stop here. After they build and they debug, everything is fine and they stop. Because most of the time, they are dealing with data processing, information processing. They do not interface with the physical world. But engineers, we build systems that interface with the physical world. You build, for example, robots, quadcopters, machines that can run by themselves. So all of this is actual hardware. So after debugging, you have to test your system in the actual hardware. You have to test in hardware, and you'll find that it may not be doing what you think it should do. That there are some errors, and then you have to think of how to solve these errors. Okay? So if it works in hardware, no problem, then you are done. Okay? This is the general flow. Very, very simplified, but these are the essential steps if to develop an embedded application. Code, build, test, test the software first, simulate, no problem. Then you test in hardware, no problem, and you're done. Okay. All right. Next one. Um, what is the difference between RISC and CISC? RISC, RISC is the R is stands for reduced instruction set computer. RISC, reduced instruction set computer. So CISC is complex instruction set computer. Okay, reduced and complex. What does it mean? Actually, this reduced instruction set computer and complex instruction set computer, this is just technology. This technology was relevant maybe 20, 30 years ago. Just like 20, 30 years ago, there is a difference between uh, mini computers and workstation. You know, a workstation is very powerful. A mini computer is just like a personal small computer that you can use, or a mainframe. You know, all these things have they are different. But today, you say mainframe, mini computer, workstation, server. Actually, it's all just the same computer, right? So in the old days, computers that is capable of executing a small set of instruction, you call that reduced instruction set computer. Example is your PIC microcontroller. PIC microcontroller can only execute 35 instructions. All 35 instructions are the same size, 14 bits, same size. ARM also makes reduced instruction set computer. In fact, their name ARM, ARM, comes from Advanced RISC Machines. This was their name initially. Because ARM, their first business was to design and sell RISC processors, reduced instruction set computer processors. Okay, just like PIC, you know. But now this name doesn't really mean anything anymore. You know, your PIC, PIC it actually means peripheral interrupt controller. In the old days, your PIC microcontroller, the company PIC, in the old days, their job was to build interrupt controllers. Okay? But now it doesn't mean anything anymore. It's just a name. Now ARM is just a name. It doesn't stand for Advanced RISC Machines anymore. Okay? Complex instruction set computers are like your 8085. Okay, if you learn the 8051 microcontroller, inside the 8051 microcontroller, you got the 8085 processor. That's an example of a complex instruction set computer. Why? Because it has 200 over instructions. And the instructions are some are 1 byte, some are 2 bytes, some are 3 bytes, some are 4 bytes. The instructions have different size and they can do a lot of different operations. Okay, so reduced instruction set computer, if you want to do complex things, you have to combine a sequence of simple instructions. But complex instruction set computer, they have an instruction for every other thing that you want to do. So one instruction is enough. But that makes the processor very complex. The instruction decoding circuit is very complex. So complex instruction set computers, they are for high performance. They are not good for low cost, low power designs. Okay? That's why microcontrollers don't use CISC. Microcontrollers use RISC, reduced instruction set computer. But the thing is, microcontrollers nowadays, their processor is approaching CISC level performance. So the line is blurring. The line is blurring between RISC and CISC. Okay, right. So the advantages and disadvantages are CISC is powerful but not power efficient. RISC is not so high performance but is very power efficient. Right. And ARM specializes in RISC processors, which is why you see all your tablets, smartphones, and all the portable devices, all of them use ARM Cortex processor, either Cortex A, Cortex R, or Cortex M. Okay? No, there is no competition so far. Now, what is pipelining? What does it mean by the concept of pipelining? Pipelining means the idea is just that pipelining. If I have a production line, if I have a production line. I have a production line. So I got this machine A, I got machine B, and I got machine C, right? So my item comes here. Machine A will work on it for, machine C will work on it for TC. And then it comes here. Machine B will work on it for TB. And then it comes here. Machine A will work on it for TA, timer. And then it's done. It goes into the box. It's done. Okay. So how long does it take to manufacture one item? To manufacture one item, you need TA plus TB plus TC. Okay. So common sense, we look at this. Hey, if I got three machines A, B, and C, why do I want to wait until I finish one product before I start on the next product, right? I can put the first item in. Let C work on it. When the first item go to B, then I can put in the second item. So I can work on the second item using machine C, and then the first item I work on it using machine B. And then after that, the first item go to machine A, the second item go to machine B. I can fit in a third item machine C. So we call this the pipeline. We call this the pipeline. And this pipeline got this example got 3 stages, A, B, and C, 3 stages. Okay, 3 stages. So effectively, once the pipeline is full, that means A, B, and C are all working at the same time. I can reduce this time. I can reduce it by 3. If TA is equals to TB is equals to TC. If the time is all the same, that means each stage of the pipeline is the same length. Then I can speed up the whole process by 3. So this is the concept of pipelining. Okay, right. So now the remaining questions. What does ARM stand for? What is ADC, DSC, SRAM? What is UART, CAN, I square, C, SPI? All these remaining questions, right? They are all theory questions. You can find their answers. They are all end of chapter question for the main textbook, chapter 1 and chapter 2. Okay, so if you go to the main textbook, is the main textbook. You can get this from the library ebook. Library ebook got first edition. First and second edition is the same one. Right? Just that the second edition got a few extra chapters at the end for IoT, but that one is not our focus. So the front part is all the same one. You can get the first edition from the ebook, or you can find the PDF of the second edition from the library, from the internet. Right? It's very easy to find the PDF. Okay, so uh, just now the tutorial one, those questions are from the end of chapter questions for this textbook, chapter 1 and chapter 2. So you can go through chapter 1 and chapter 2, just read it and try out the remaining questions now. Okay, right. Do you have any questions before we stop here? Okay, right. Thanks everyone for coming today. Have a nice weekend and I'll see you next week. Okay, so that's all. Thanks everyone. Bye.